This presentation has an application of the formulas that we've developed in the previous presentations of this series. Specifically, we're going to be applying our formulas to the half wavelength dipole. The half wavelength dipole is a type of antenna that is used for radio amateur and other uses, so it's quite useful. So from previous derivations, we know that the electric field in the theta direction is equal to I times the characteristic impedance times I naught e to the minus ikr over 2 pi r times an interesting term called cosine kl over 2 times cosine theta. So that's the cosine of the cosine term minus cosine kl over 2 quantity divided by sine of theta. For a half wavelength, case, we have k, which is the wave number, 2 pi over lambda, and then L, which is equal to lambda over 2, implying that KL over 2 is equal to 2 pi over lambda times lambda over 2 times 1/2. So here we have some cancellations. The lambdas cancel, the 2's cancel, and we're left with KL over 2 equaling 2 pi over 2. So E theta then simplifies to I z naught I naught e to the minus I kr over 2 pi r times cosine of pi over 2 times cosine of theta, so that's the cosine of the cosine term, divided by sine of theta. Notice that the second term, KL over 2, it's the cosine of that. Cosine of pi over 2 is 0, so it goes away. Similarly, we can go ahead and come up, starting from our value for the electric field, we can come up with the value for the magnetic field to be H phi approximately equal to I times I naught e to the minus ikr over 2 pi r times cosine pi over 2 cosine theta divided by sine theta. So if you remember, we then went to the Poynting vector, which is going to give us the power. So that's 1/2 times the real part of the following product. Electric field crossed into magnetic field complex conjugate. And that equals to z naught I naught squared over 8 pi squared r squared times the cosine of pi over 2 cosine theta divided by sine theta, that entire quantity squared, times the unit vector in the r direction. And that's the Poynting vector average. So it follows then that if we integrate that over a surface, we get the complete power, the total power radiated, which is equal again to integral over that surface of Poynting vector averaged over the entire surface, which equals to z naught I naught squared over 4 pi times the integral of 0 to pi cosine squared pi over 2 cosine theta divided by the sine of theta, d theta. Now that looks very impressive, But remember that that's a definite integral. So you can think of that entire thing as one number. So that should help us out considerably. So the next step that we're going to do is we're going to evaluate that integral using a program that's available online, and it's called Wolfram Alpha. Now there are other programs available online, and there's ways you can integrate that in other ways, but I found that Wolfram Alpha allows you to go ahead and just pretty much type in the integral from 0 to pi of this value, and it'll go ahead and evaluate that for you. So that gives you that the radiation power integrated over the entire sphere for the half wavelength dipole equals to Z naught I naught squared over 4 pi times this value, this number, 1.21883. Again, we got this number using Wolfram Alpha to integrate that definite integral. Okay? So the other thing to note here is that from a previous presentation, we did define resistance of radiation, the radiation resistance, to be equal to Z naught over 2 pi times the value of that integral, which in this case is 1.21883. So for the half wavelength dipole, it turns out that that is the value of the radiation resistance, which then sums to the ohmic losses in an antenna. As the current is going up and down in our dipole antenna, we're going to have radiation resistance going out into the atmosphere, but we're also going to have ohmic losses in the, heating up the antenna and such. So this is just a term for the radiation resistance of our dipole antenna, and that comes out to be, remember, Z naught is the characteristic impedance of the vacuum. So that's mu naught over epsilon naught square root. Those are constants that you can look up, and that gives us 377 ohms. So since we have that, then we have 377 times 1.21883 equals to that, divided by 2, divided by pi, equals to 73.13. So the radiation resistance for a half wavelength dipole antenna equals to 73.13 ohms per our derivation. So that's interesting to know, because many times we're given a value of an antenna, of a dipole antenna, the input resistance is 73 ohms. Well, we've just shown exactly where that number comes from. So it's not just out of thin air, it's actually out of the mathematics. So that's where the 73 ohms comes from. I hope you found this useful. Thank you.